If the ATP synthase is not part of the electron transport chain, then what is it part of?
Well, many people confuse the ATP synthase as being part of the electron transport chain, when really it's actually responsible for chemiosmosis, which is, to be specific, it's actually the transport of ions across a selectively permeable membrane. It's a mouthful. Anyway, do not get mixed up by its appearance in most electron transport chain diagrams. The reason that it's often put inside the same diagrams is because the whole process of electron transport with the ATP synthase is what makes up the oxidative phosphorylation pathway.
So oxidative phosphorylation describes the whole process of electron transport, proton movement across the membrane, and ATP generation. But what is with all of the other protons collecting into intermembrane space?
That's a great question, and the reason is really simple. When electrons are passed through these protein complexes, protons are pumped from the matrix side of the membrane to the intermembrane space. The electron carriers, NADH and FADH2, lose their hydrogens when they reach their respective complexes and become oxidized.
An easy way to remember if a molecule has been oxidized or reduced is through the mnemonic LEO. The lion says GER. Lose electrons oxidation, LEO. Gain electrons reduction, GER.
Okay, so now we understand oxidation and reduction, but now let's focus on the protons being pumped across the intermembrane space. Do you think it's through active transport or through passive transport?
Well, we know that the protons are pumped across the membrane when the electrons pass through the complexes. So the protons must be using that energy provided by the electrons to move across the membrane.
Oh, okay, I think I understand. So, since energy is being used to pump those protons across the intermembrane space, we must be using active transport.
Yes, so since we have a high concentration of hydrogen ions or protons in the intermembrane space, then that's right. But I have to wonder, does their charge or the fact that there's so many on one side create any type of driving force?
Actually, that's exactly what happens. Since we have such a buildup of hydrogens, which creates a large concentration gradient, we also have they all have charge. Let's keep that in mind. Charge and concentration gradient. So we have a large electrochemical gradient being built up on one side of the membrane. Nature has a tendency to want to equalize concentration and charge gradients on both sides of a semi-permeable membrane, which is exactly what the lipid bilayer is. So an electrochemical gradient is established and a proton motive force results.
So what you're saying is that the hydrogen ions want to cross back through the bilayer and back into the matrix because there's so many of them on one side of the membrane.
Yes, this process will occur through facilitated diffusion and not active transport.
Okay, so the protons can go back through the protein complexes of the electron transport chain, but they can go back to through the ATP synthase protein complex.
Right, and as they travel through the ATP synthase complex, a portion of the protein will start to spin and therefore generate ATP. So what you may be wondering is, what would happen if we uncouple the ATP synthase protein from the electron transport chain? Well, the uncouplers, like thermogenin, prevent the establishment of a proton gradient, and thus no ATP is generated, and energy from the electron transport chain is lost as heat. So now that we've reviewed glycolysis, the Krebs cycle, and the electron transport chain, let's try and make a model of the whole entire electron transport chain mechanism. So what we're looking at here is the phospholipid bilayer, which separates the mitochondrial matrix, this side, from the intermembrane space. Within the lipid bilayer, we have 5 membrane proteins. But before we get into that, let's first review briefly what makes up the lipid bilayer. We're representing the polar heads with these little balls, and these purple tails are going to represent our hydrophobic nonpolar tails. The reason that the polar heads, by the way, are hydrophilic in nature is because there's a negatively charged phosphate group. So now let's go ahead and place our protein complexes in the lipid bilayer. So here's complex 1. Now we got to put in complex 2. Actually, let's put complex 2 a little bit further, right there. Let's put complex 3 in. Finally, complex 4, all the way here at the end. Remember that the ATP synthase protein is not part of the electron transport chain, but is the last step of the oxidative phosphorylation process where we generate ATP. So the complexes that we've laid down so far, this is part of the electron transport chain. the part of chemiosmosis is represented by the ATP synthase protein, which we're going to place all the way at the end. So the ATP synthase protein plus the electron transport chain equals oxidative phosphorylation. So now let's focus on where those NADH molecules that we've generated from glycolysis and the Krebs cycle go. So we're going to represent our NADH molecules with these little purple cotton balls. So we'll put a couple of those on the matrix side. And every single time the NADH molecules approach the intermembrane molecules of the lipid bilayer, they give up their hydrogens, or rather their protons, and become NAD+. So as we have a couple of them giving up their protons and becoming NAD+. So here's an NADH approaching the protein, gives up its proton to the intermembrane space and becomes NAD+. The electrons of what was previously the NADH molecules then get transferred all the way down the protein complexes until they finally reach complex 4, where water is produced and oxygen serves as the terminal electron acceptor. Similarly, FADH2 that we discussed earlier, which was also produced in the Krebs cycle, are going to be represented by these green cotton balls, and they are also on the matrix side. They also serve to pump protons across the lipid bilayer. So eventually what we get is a lot of protons on one side of the lipid bilayer, and this causes a proton motive force to form. So here we have all of our protons, which are going to represent obviously with these blue little marbles. And remember that we talked about earlier how nature has a tendency to equalize concentration gradients and even charge on both sides of a semi-permeable membrane. So here we have a lot of charge and a high concentration on the intermembrane space side, but we really don't have that much concentration of protons or of charge on the matrix side. So to solve this problem, we're going to take our protons, and we have our ATP synthase protein over here, and every single time, it's going to take these protons and rotate. As it rotates, the energy produced by these protons moving across the different sides of the bilipid membrane form ATP, which we're going to represent by these yellow cotton balls. So the ATP synthase is not working through active transport, but rather through passive transport. Through this process, we can see that all of the protons are getting back on the matrix side and ATP is produced. And this entire process is oxidative phosphorylation.
So now we have reached the end of the ATP generation process, but I'm still wondering about how much ATP have we really generated per glucose molecule?
That's a good question, and in order to actually review all the steps we've gone through so far, I think it would be a good idea if we actually pull out a diagram of all of the different steps and go through it slowly. So if everybody has their diagrams in front of them, fill it out as we go through each step. So let's begin. For every molecule of NADH that was oxidized by complex 1, 3 ATPs will be generated. And for every molecule of FADH2 oxidized by complex 2, 2 ATPs will be generated. So let's try and recall how many of each molecule we generated and used in each step of metabolism. During glycolysis, we generated a net yield of 2 ATP through substrate level phosphorylation and 2 NADH molecules. Then we transported our pyruvate and NADH molecules into the mitochondria, at which time we lost an ATP for each NADH transported. During each turn of the Krebs cycle, we generated 1 ATP, 3 NADHs, and 1 FADH2 molecule. Since we have 2 molecules of pyruvate that were converted to 2 molecules of acetyl-CoA, we went through the Krebs cycle twice. And finally, we generated 30 ATPs from 10 NADH molecules and 4 ATPs from 2 FADH2 molecules in the electron transport chain. Remember that each NADH molecule yields 3 ATPs and that each FADH2 molecule yields 2 ATPs. So overall, we generated 38 ATPs from 1 molecule of glucose. But don't forget that we spent 2 ATPs while transferring our NADH molecules into the mitochondria. Therefore, we actually gained 36 net ATPs.
Wow, 36 ATPs generated per glucose molecule? That is a lot of energy.
I know, right? Cellular respiration is incredibly efficient, and all of the NAD plus and the FAD plus molecules that we generated from oxidative phosphorylation are actually going to be re-reduced by the glycolytic and the Krebs cycle pathways. Therefore, we can keep generating ATP.
Well, it seems like aerobic metabolism is definitely preferable, seeing as we get so much ATP. But about how much ATP do we gain when oxygen is not available, like in fermentation?
Well, when oxygen is not available, glycolysis can still occur. But the Krebs cycle and the electron transport chain, pyruvate can't go through those anymore. So instead, pyruvate gets converted into organic molecules, like lactic acid. If any of you have ever gone running or done any type of physical exercise, that burning sensation that you feel in your muscles is actually due to a buildup of lactic acid, since our muscles are struggling to reach oxygen and actually gain ATP. So we're relying on glycolysis at this point. Remember that we also generate 2 NADH molecules from glycolysis, and that we need NAD+ in order for glycolysis to continue running, and thus to keep generating ATP.
Wait, if you're saying that glycolysis produces NADH, but we need the NAD+ in order for glycolysis to continue, how do we regenerate the NAD+ molecules that we don't when we don't have the electron transport chain or the Krebs cycle?
Great question. And actually the answer is that the conversion of pyruvate to an organic molecule like the lactic acid that we were just referring to oxidizes NADH back to NAD+. Therefore, glycolysis can continue running, but we're still only producing 2 net ATPs.
Wow, so we only generated 2 ATPs in fermentation in comparison to the 36 ATPs that we generated in aerobic respiration.
Right, and the whole process that we just discussed so far was called lactic acid fermentation.
So as a review, when my muscles get sore, it's because they no longer have access to oxygen as readily as they do when I'm sitting down, and my muscles switch to fermentation for energy. As a result, the lactic acid buildup causes discomfort and fatigue in muscles after prolonged exercise. Right, well, I think we've had enough of biology for one day, but we'll finally feel like we understood cellular respiration. So,
I agree.
Good
luck,